everyone. My name is Tamir Shul. I'm a PhD candidate from the Technion, and I'll be presenting our work, Adversarial Robustness in Parameter Space Classifiers. So I'll start with just some definitions that I'll be working on during the presentation. So first of all, neural representations, I assume everyone knows them, but generally I refer to INR as a representation of a signal using a neural network instead of the standard common grid-based representations, like you can see in the example below. We have an image and it's represented by some trained neural network that is trained to represent this image specifically. So generally, these INRs have been garnering a lot of increased interest in recent years, mostly because they allow compressed data representation that is also very flexible. With the power of representing via a neural network, we can inject some mathematical traits that are desired. So people are showing more interest in such representations. Now, specifically, because of this growing interest, some works, specifically the functa that I'll show in this paper, show that we can achieve a variety of downstream common tasks in deep learning, like segmentation and classification and generation, directly in weight space, meaning directly over the weights of these neural networks that represent each data within a data set. Specifically, we'll be working in this paper with functas because they allow a more lightweight representation. So what functas do is, given a data set, they optimize a center of mass for the entire data set, a single neural network, and then optimize per sample, meaning the neural network that would represent each datum in the data set, by optimizing a modulation vector that conditions the biases, the set of biases of the neural network that represents the specific datum, and the weights are shared across the entire data set. So this modulation vector can be the size or dimension of this vector is to our control, and this allows more flexible representation in terms of size. And of course, after we have these modulation vectors, the downstream deep learning task, in our case classification, opts directly over these modulation vectors. So what we do in our work is we explore the adversarial robustness of such weight space classifiers, meaning classifiers that receive as input these INRs, or in our case, modulation vectors of functas, and try to output a classification. And we think it's very important because there has been a lot of growing interest in such deep weight space classifiers, but very limited work has been devoted to exploring the adversarial robustness that is known from computer vision, general computer vision, to be a major concern in such deep learning algorithms. So what we do is we develop a suite of adversarial attacks that address the specific needs of an attack in deep weight space. And we actually observe some, perhaps surprising, perhaps not, adversarial robustness that is inherent to these classifiers, especially when compared with common signal domain classifiers. So I'll shortly introduce our threat model. So what you see here is we apply most of our attacks in signal domain because we assume that the attacker has access to signal domain. But basically, the reason for this assumption is that the modulation optimization, the optimization of each modulation vector for the specific datum, specific image, for instance, is controlled by the user and not by the attacker. So we apply our attacks in signal domain, and we apply the constraints of the attack in signal domain. So like you can see here, we add some perturbation onto our image in signal domain, then we optimize a new modulation vector that would represent this image after the perturbation. This is, of course, being done with the set of optimization steps, that is to the control of the clean user, meaning not the attacker. After we have this optimized modulation vector, we freeze it and feed it into the classifier that opts in INR space, and take the class logits and backpropagate through to the perturbation applied in image domain in order to optimize the attack and mislead this classifier. So one major important notion here that we must address is that we need second order optimization, and I'll explain why. When we backpropagate the error incurred by this perturbation over the classifier's accuracy, we have to backpropagate through this optimization process that is being done per perturbation for finding the modulation vector that represents the perturbed image. Now, this requires second order differentiation, which is heavy and expensive. And this is one thing that we address in our slide of attacks. So we developed five different adversarial attacks. The first one is termed full PGD. In full PGD, we simply backprop through the entire set of modulation optimization steps. So when I say modulation optimization steps, I mean this little window here that I showed in the previous figure. We backpropagate through the entire set of steps. Now, of course, this greatly inflates the computational graph and incurs computational and time costs for the attacker. So we also propose some attacks that are a bit less accurate, but tend to be more cheaper in terms of computational resource and also less prone to exploding gradients and vanishing gradients. So the first one is TMO. In TMO, we only take the last tau for some hyperparameter tau, the last tau steps of the modulation optimization process, and only backpropagate through them, very similarly to what people do with backpropagation to time that we see in RNNs. Specifically, the shortcoming of this TMO method is that we only take a subset of the modulation optimization steps, meaning the attacker is less informed, and therefore we also propose bottom, which is slightly more expensive in time, but slightly more accurate. And in bottom, we segment the entire N modulation, full modulation optimization steps onto tau segments, each of size N over tau, and we only backpropagate through these little segments. So if we have, say, 100 modulation optimization steps, and we chose tau to be 20, then we have for each set of 20 steps, 0 to 20, 20 to 40, etc., we perform backpropagation and update our perturbation. The fourth method is ICOP. In ICOP, we want to also explore attacking and perturbing in the INR domain, in the modulation vector domain, rather than in signal domain. Now, the challenge here is that we still need the constraints to be applied in image domain because we don't have the notion of constraints. We don't know how to constrain modulation vector because we want the constraints to be linked in some way to human perception. So what we do is we let the attacker optimize and perturbation in the INR domain. And then after the attack is optimized, we take some gradient steps that are orthogonal to the classifier loss that would retrieve, meaning get the response of this perturbation in our domain, the signal domain response, and make it fall within the set of constraints that are, of course, applied, as I said, in the signal domain. The last method we have is implicit differentiation. So we can approximate the entire set of modulation optimization steps using fixed analytical expression, given that we assume some optimality conditions. In our case, we assume a local minimum in our fidelity to the original signal as given by the siren or INR representation. And the upcoming, the upside is, of course, that we don't have to backpropagate through a lot of optimization steps. The shortcoming is that this method only works as good as our optimality conditions and how well they hold, meaning if our representation error is large, implicit differentiation would not work. So I'll shortly introduce our experimental setting. So we have, for all attacks, we experiment with PGD attacks with L infinity bounds for 100 PGD iterations. We first, of course, train a clean classifier for each of the dataset. We experiment with 3 datasets, MNIST, Fashion MNIST, and ModelNet 10. Of course, we would like to experiment in the future with more challenging datasets, but for currently the state of the art of C410, C4 100, and ImageNet, and more challenging datasets like these ones, we could not get good enough clean classification accuracy in order to credibly measure the effect of adversarial attacks. So we have MNIST, Fashion MNIST, and ModelNet 10, which is a data set of 3D meshes, which is the more, let's say, common case for using INRs, because the data is larger. And we also compare our results with conventional classifiers that operate in a single domain. And to do this, we train a set of autoencoders that would encode these single domain data, and then train a classifier to operate in their encoded latent space. We mostly experiment with CNNs and vision transformers because they are the most common. So I'll show some results. The upper table you see here is the results for 3D data, meaning we apply a voxel bit flipping attack over our voxel grids in 3D data from ModelNet 10. What you can see here in the flip ratio column is the percentage of bits we allow the attacker to flip. Of course, the attacker needs to optimize which bits to flip. And for 2D data, we apply attacks with L. So this for 3D data, we actually use the L0 bound. For 2D data, we use the L infinity bound, and you can see here the epsilons are the bounds before being divided by 256. And I think the trend, regardless of specific numbers, the trend is pretty much consistent. We see that we have relatively large inherent adversarial robustness for a classifier. So it is true that, let's say, for fashion analyst, we have the largest bound of attack reached 34%, and here we have 41 for the 3D data. But still, when you compare to single domain classifiers, the difference in the success of the attack is very large in favor of the white space classifiers, I will show now. So what you see in the right diagram is for 3D data, we can see that the black curve represents the classification accuracy as we increase the bits flip ratio of the attack. And we can see that there's a very big difference between a signal domain classifier and our white space classifiers that are the colored ones. The same trends, we can see it for the fashion analyst data set. The dotted curves are for signal domain. You can see we have vision transformers and CNS, and the continuous curves are for our SWATA 5 attacks, and all of them achieve better accuracy for every bound compared to the signal domain classifiers. And we can see even pretty large difference. Another set of experiments we perform is qualitative. So we generally in computer vision, we know that the effect of one of the reasons adversarial attacks work is that we apply some bounded small perturbation in the input domain, in the input space, and the network amplifies this perturbation so that in the output or in the final layers, we get very high responses, and this is how these attacks mislead classifiers. So what we do is we measure how the attacks that we apply for signal domain classifier, parameter space classifiers, and signal domain classifiers are being amplified throughout the layers. So what you see in the left diagrams is for weight space classifiers. Layers 0 through 10, meaning the first 10 layers, are INR, meaning the siren, the whatever representation we have for the signal, and the last 3 layers are the classifier that receives the modulation vector. So we can see that even though this perturbation is being amplified by the INR, because the training of the representation of the INR and the classifier are disjoint, and this is our hypothesis for why we have adversarial robustness, we can see that the amplification is very much attenuated when being fed into the classifier, meaning the amplification incurred over the siren, over the representation, over the INR, does not affect the classifier as much. You can see this very big decrease in amplification in the 10th layer. And this is consistent for MNIST and fashion MNIST. In contrary, when we look at the signal domain classifier, we can see very large amplification. The layer, there's a slight error of the location of the dotted line, but for the second layer, this is the layer of the encoder. We have some CNN encoder here, and we also experimented and saw similar results with vision transformer. Before the classifier, we can see that between the encoder and the classifier, you have very big amplification. This is layer 2. So the amplification becomes much larger. And we measure this amplification by the norm of the ReLUs after some linear layer. So this is another evidence for the adversarial robustness that we observe. Finally, we also look at the encoded latent spaces. Of course, when we look at the single domain classifiers, we look at latent spaces. When we look at the weight space classifiers, we actually look at the set of modulation vectors, the space that is formed by the set of modulation vectors that condition our sirens, our representations. And we can see that, first of all, in each of these two diagrams that you see in each of the two plots, the two left sub-figures indicate what happens when we have clean modulations, meaning we haven't activated any adversarial attacks. You can see that the latent space is pretty much well structured. The classes are well separated for both signal domain and weight space classifier. This is what you see here and here for MNIST and fashion MNIST. Of course, when we apply adversarial attacks, we can see a very large difference between single domain classifiers, the latent spaces for single domain classifiers, where the separation is very much damaged, And in contrary, when we look at weight space classifiers, you can see that the separation is almost completely the same. So this is another evidence for how how we have an advantage for weight space classifiers in terms of the structure of latent space. I'll skip limitation in the future work because I see I'm out of time, but of course I regret not being able to attend, and I encourage everyone who is interested in our work to send me an email, and I'll be happy to collaborate, and that's it. Thank you.